understand the new type of the structure called truss structure. So we already talked about this structure. In fact, in one of the midterms, you had some sort of truss mechanism to transfer the load, but we were not interested to find internal forces in this structure. We were only interested in find external reactions, and then we use our 5-step algorithm to solve. Right? Today again we have 5-step algorithm, but we try to simplify this to a particular subclass, the called method of joints. So step 1 was choose the system. Step 2, draw FTD. 3, write the equations. 4, solve them. And 5, verify your results. Okay. So now, for this particular structure, these 5 steps reduce to a very simple algorithm called method of joints. Right? Later on, you choose a different kind of system and reduce it another set of algorithm called method of sections. So before we do that, what is a truss? The definition of truss. Truss is a lightweight structure that is composed of bars that are connected together with a set of pins or joints. And assumption, the main assumption is that the joints are frictionless. So in fact, this is a schematic. Always in the book, when you see the truss problem you want to solve, the plot is like this simple. It's a schematic plot. So I want to draw an actual connectivity drawing here. So let's consider this member here. So if you draw it, that member is kind of like this. Just draw it straight. That member is like this. And this thickness is very small. It's a rod or bar. So in fact, this member cannot accept a shear load. V shear load. So if you apply a shear load like that, it's going to break according to the assumption we have for truss. So truss is composed of bars that their thickness is very small. So the load you put in this load is either this way, tension, or the opposite direction, compression. So it's always axial. That makes the analysis very simpler. If you had a beam instead here, you remember we solved beams and frames? Then you could have a load like that. In fact, like previous example we solved, you could have even the distributed load, shear, vertical. And you're going to have all kind of internal shear force, moments, whatever. We will study in the next class, we study the internal load. Right? But here in this, because the thickness is small, they assume that this structure won't be able to accept the shear load. So, because this thickness is small. T is small, because it's a small value. Right? So your load is always like this. When you draw FVD, the load is axial, right? So another thing I want to say, to analyze any structure, we have 5 steps, as we explained before. In this case of truss structure, we can simplify these 5 steps by assuming that the system with all joints or pins. Right? In fact, for example, this connectivity here, consider this, then you have, let's number this, bar 1, 2, 3, 4, right? Then you have another bar here, another one. And another one there. Right? So this is 4, 3, 2, and 1. If you put all of these all over each other and have a pin, this is a pin, right? So if you put all of these on each other and then put this pin in the hole, and assume that there is no friction, then this is called this pin connection or joint connection is happening everywhere in the truss. Now, if you choose that pin as a system, so when we say method of joint, our objective is to draw FBD for this pin at this location, and also there is another one here, and also there is another one here, and here, and here. See that? So when we say solve this problem using method of joint, that means that don't think about the choice of system. Automatically, your system is all pins or joints. That's the reason we say method of joint. Then the rest of it is pretty much the same. You draw FBD, write equations, solve them and verify. It's nothing new. Today we're talking about nothing new. So let's go ahead and solve one problem immediately. Go to page number